Okay, hi and welcome everyone to this 1W-Minds seminar. Today's speaker is Yura Malitskyi. He obtained his PhD from Kyiv National University in 2015. And he is now at Universität Wien, University of Vienna. And before joining Vienna, he has been in Göttingen, Graz, Lausanne, and also Linköping. Yura's research resides in continuous optimization, relating to many different things such as dynamical system, optimal transport, and machine learning. And today he's going to talk about adaptive first-order algorithms for convex optimization. The floor is yours, Yura.
Thanks a lot, Axel. Thanks a lot for inviting me here and for providing me this opportunity to talk about. So please free to interrupt me at any moment you'd like to ask questions, either orally or just write something in the chat, and then Axel would read your question. I think we have plenty of time. I didn't expect that you're so generous, and I could speak for 1 hour, and afterwards, we can have a discussion with many other questions. So I will try to be slow because not everyone kind of may be familiar with optimization. So don't worry, there will be not so many definitions and so on, but still it's better if you really understand everything. So I will talk about adaptive first order algorithms. And this is a joint, this work is based on 2 papers and both are joint with Konstantin Mishchenko. So we'll study, in the beginning, we'll study the most simple optimization problem. It's unconstrained minimization. The function f is convex and differentiable. What can be simpler, right? This is a foundational problem. And just to fix notation and some definitions, we will say the function is L smooth. We will always will mention this, which is equivalent to say that its gradient is L Lipschitz, which means that this inequality holds for all x and y. So we have some global control over how fast gradient changes, let's say. So this is like L smoothness of the function, but sometimes it's more useful to talk about the gradient. So we will just interchange and switch from one thing to another. Whenever we use star notation, either for x or for f, then it's always about solutions optimal. Since we have convexity, all these f stars are the same, so we don't care about at which point it happens. But of course, there may be many solutions x star. So whenever we talk about the star, fix the star is something about the solution. Okay, so this is basically all you need to know. And the foundational algorithm for this kind of problem is, of course, gradient descent. Most likely, you'll all know about it. Where alpha is some positive number, is a step size. And we have the following result for gradient descent. So if you assume just a little bit more than convexity, we also have this like L smoothness, means that we have control over the gradient. And if we pick step size small enough, so that let's say it's smaller than 2 over L, then we have convergence of each raised to S solution. And also we have a nice rate for function values. We have 1 over K rate. And if you want to see the dependence on the step size, then step size in the denominator. So the smaller the step size, of course, the worse convergences, so linear proportion. So this is well known, right? You cannot improve this rate, so it's tight for gradient descent and so on. So the natural question is, of course, this is like the best what you can do with this kind of algorithm. Maybe a small modification of this algorithm will give you something much better. We should understand what is the limitation of this kind of method. And in general, there is very interesting result about lower bounds. So let's say if you're talking about some abstract algorithm and we just say it's a first order algorithm. By first order algorithm means that we just use first order information, meaning function values and the gradient, not hashes, not this stuff. So we stop on the first 2 terms of the Taylor expansion. So if our dimension is high enough, then there is some nice convex L smooth function. So for any of this kind of first order algorithm, you cannot beat than some constant divided by k over square. So you cannot get better than this kind of stuff because you can just construct a very bad quadratic function so that any of this kind of first order algorithms, they won't be faster. That's how you show it. But still, right, previous algorithm gave us 1 over k. And this result says us something about C over K square. So there is still this discrepancy, this gap. So the natural question is, okay, can we actually approach to this C over K square? Can we find another algorithm? And of course, the answer to this is well known. It's yes. It's basically Nestor famous accelerated gradient descent says that if you introduce a sequence yk, basically a perturbation of your iterates xk, and you do gradient descent not from xk but from this perturbed iterate yk, and you perturb it in a very clever way, then you can basically, so it's computationally is basically the same as gradient descent, but for this method you can show that under the same assumption, you can say that whenever a function is a small, step size is also small enough, then you also have convergence to iterate, but the rate now instead of 1 over k is 1 over k squared with the same dependence on the step size. So basically the same as we had before, just k is changed to k squared, much better. And of course now this result matches a lower bound, so basically we can stop. Right? We did everything. You cannot improve this result. So this is like a classical convex optimization. But still, in fact, both these methods are not perfect. So there are still questions open. So, and for instance, what kind of drawbacks they have? Both methods, if you see, they use a fixed step size. The step size was dependent on the Lipschitz constant, and this Lipschitz constant is basically a supremum over all space of this quantity, difference of gradients divided by difference of x minus y. And this is a bit also strange, right? We start from x0 somewhere, and we would like to converge to x stars that we don't know where, but definitely we are not going to explore the whole space, right, or the whole domain of the function. We kind of like we will work more or less locally in some part of the domain. So it's a bit strange that we have to use this global information about the function f. And of course, the idea is the larger domain you have, the larger Lipschitz constant will be, so the kind of the smaller step size. So the idea, if you could use this local information about your Lipschitz constant, some local estimates, so maybe you could use this step size here larger, and if this larger step size, you will converge fast. So that's the idea. The second thing is, like whatever you do, you still need to implement this algorithm, either accelerated gradient descent or just gradient descent. So you need to pick this alpha, and either you do it by like trial and error, or you devise some extra thing. So or you have to estimate this Lipschitz constant L, which for sure for many complicated functions is super expensive. Or all your estimates would be like very conservative, then the step size will be very tiny, and again you lose in performance. And finally, there are convex functions that basically just are not L smooth. So this L can be plus infinity, let's say, like if you have exponential function, right? It is not globally L smooth because it increases too fast. So unless we have a compact domain. So for this kind of functions, also it would be interesting what kind of result we have for gradient descent. But the series says that we need this L smoothness. Okay, so this is also, of course, super well known. So, and definitely there are some solutions how to approach, how to tackle this issue. So one, and probably the best one, the most universal one, would be line search. So let's say if you have no idea which step size to take, then start from some step size, do your gradient descent. I'm showing here for gradient descent, but more or less the same can be said about acceleration. So you have no idea about which step size to take. You take anything, you start from it, do gradient descent, and check whether some inequality holds. Because if this inequality holds, because that's exactly why you need the step size small enough. So if it holds already, then you say, my assumption about, I accept my step size that I guessed, and you continue to the next iteration. If the step size was too large, then this inequality does not hold, and you just go back and repeat the same thing. So it's basically you have now, instead of one for loop that was gradient descent, you'll have two for loops. One is for iteration, and one is this insider procedure to check whether step size is good enough. So it's really reliable, and in software, indeed, this is basically a how you should do it. But it's clearly that it's one iteration of a gradient descent is more expensive because you have no idea which step size to take. So you can run many these small iterations, kind of sub iterations. So we just increase the cost per iteration. But otherwise, it's a good approach and reliable. There is, I think, as a Pollack step size, very interesting approach. And it says that you have to choose step size in the following way. You take alpha k as fxk minus f star divided by the square norm of the gradient. This method works perfectly, but the drawback, of course, that you have to know this f star. F star is this optimal value of the function f, and sometimes, indeed, you do know it, even in advance, without solving the problem. You know that f stars, let's say, has to be 0, because you know that there is solution, and it says something like least squares or nonlinear least squares, whatever. Because people like to say about it's not convex anymore, but let's say if it's over parameterized neural network, the loss function has to be near 0, this kind of arguments. So this also can work pretty well, but this also works for convex problems. So that's why with neural networks it's a bit far-fetched. So the drawback is basically we need to know f star. In many practical problems, f star is not available, and there is no way we can guess it. So that's why it's also not super practical. There is a famous Berzeliai-Bravais step size, which so this alpha k is something with gradients, xk, some inner products. So not clear why, but the motivation was to do something with like to approximate Newton step or like quasi-Newton step. Unfortunately, so this is very popular approach, but somehow even surprising that it is that popular because there is no guarantees in general for nonlinear optimization, and it's very easy to construct a very nice convex, even strongly convex function where this method will fail. And so the only guarantees that are really reliable, interesting, they are for quadratic function f, where this method can work pretty well, but in general not. And we're interested also in this theoretical stuff, of course. And then there is a famous family of other graph algorithms that inspired many algorithms in modern machine learning from optimization perspective. And I am not going to write it in full generality, but let's say it's the simplest kind of method. We would like to estimate the step size. Sometimes we would like to estimate the precondition or the Hertzian, but in this case, it's just a scalar for simplicity. So we consider this summation of the squared norm of gradients, divide by them, and this is kind of our step size. So this method also can work pretty well, but it's not super adaptive. Also, adaptivity even in the name of it. For instance, for this particular instance of the algorithm of the family, you have that vk, the sequence of square norms of gradients. It is increasing, so it means that the step size b divided by square root of vk is decreasing. So it's kind of a bit strange, right? Because there is no reason to believe that our step sizes with time have to decrease. So in some sense, it can adapt at some point, but not forever, right? It's somehow, or maybe even it's even counterintuitive, because if you assume the flat function, a convex function, it looks like this. So basically, near solution, it should be flatter, kind of, unless there is some weird stuff is going on. So the gradient has to be even smaller. So the step size you would like to take even larger. So that's a drawback of this kind of approach. And also, you need to tune B, because these algorithms, at least from a performance side, these algorithms are very sensitive to this B. And there is no way, like you have no idea how to choose this B. So still there is this issue. Okay, so probably there are some other approaches, but this is basically the most general one. Okay, now, so we have the same problem. F is convex, differentiable. Let's recall that this is our gradient descent. This was the guarantees for convergence. So if step size is less than 2 over L, and let's recall what is L. So F is L smooth. If this L constant L, the ratio between these two quantities is fixed, is finite. So now your goal is you have a computer and you need to solve some problem with gradient descent, and you have no idea how to pick step size. So, and you would like probably maybe to make it a bit faster. So most likely, if you think like for 5 minutes, and you don't care about theory, you just think about you have like 5-10 minutes. You need to implement the algorithm as fast as possible with hope that it will converge to a solution. So very likely that you will come up with something like this. So instead of global L, you compute LK in every iteration, and you have already gradient, you have previous gradient. So kind of instead of this X and Y that are like some arbitrary over, you just take XK and previous XK minus 1 and divide by XK minus XK minus 1 and use step size 1 over LK, the same as like for gradient descent standard. So I hope it's like, at least it sounds like it's a reasonable approach, right? There is nothing that's like really counterintuitive. Or if you're like me, a bit on a more conservative side, then you can say maybe 1 over LK is like too optimistic. Like who knows how my function, and maybe it's like with a fix it works, but like with 1 over LK it may not work. So maybe you would like to introduce some damping factor P larger than 1, maybe 2, maybe 10, just to make it slightly smaller. So because with a smaller step size, there is more chance that your algorithm will converge. But it is some arbitrary number. You just feel whatever you think. So on the left-hand side, we have a very reasonable algorithm. What is interesting is that this algorithm will never work. So we have the following result. So there is a nice convex one smooth function f. So Lipschitz constant L is 1. So that whatever constant p is this damping factor you choose, larger than 1, there will be some initial point x0. So if you start from this initial point x0 with gradient descent, the algorithm will diverge. So this is like very simple rule, kind of, it cannot work theoretically. But of course, I'm pretty sure whenever you need to really solve some problem in practice, and you have like this 5-10 minutes, if you implement it, it will work. Because for sure you will not find, and it's very unlikely that your practical problem will be exactly like a counterexample in this theorem. So if you need, you can still use this rule, and it will be most likely perform very well in practice. But so the algorithm we proposed actually is super close to the one you see on the left that doesn't work. So it's in the red box, and if you compare them, basically first 2 lines are exactly the same, and only the third line is different, how we define the step size alpha k. So the only kind of difference here is that we have this red term that tell us that we can increase alpha k, right? Alpha k can be larger than alpha k minus 1, but we have to control how fast it increases. So you have this strange thing, 1 plus square root of 1 plus something, the ratio of previous one, and this is how much you can increase. You can increase it like more than this. And the second term, 1 over 2 LK, of course, is basically the same as on the left-hand side, just with P equal to. So it's kind of this exactly the same as before, plus some control how fast step size can change from one iteration to another. And if you think we understand why you have this term, unfortunately, I have to disappoint you. We also don't understand why we need to control how fast it changes. It follows from the analysis. I will try to explain how we came up with it, but it's not a really satisfactory answer, I would say. So there is no kind of intuition why we really need this. Okay, up to this point, do we have any questions? Okay. So let's go. Let's repeat again. So this is algorithm in the right-hand side. This is algorithm, and now we go step by step to explain everything. So we have the case iteration. In the case iteration, we have our current iterate xk, we have previous gradient, and we have some scalar theta k minus 1. The theta k minus 1 is just a ratio between the step sizes for simplicity, for notation. So first we compute gradient, which is kind of the only expensive operation in gradient descent, right? It's like you have to compute gradient. Then we compute LK, but this is a cheap thing. You just reuse previous gradient and just operate with vectors. So it's not much different from the previous gradient descent. We substitute now this information into alpha k, compute it. And finally, we update our iterate xk, and we obtain xk plus 1, and we update theta k, which is a ratio between step sizes. So overall, is basically the same, computationally is the same as previous, like classical gradient descent with a fixed step size, right? Because still we need to compute only one gradient descent, only one gradient, there is no line search procedure, and so on. And all this extra thing is like super trivial. Okay, so what kind of result we have for this algorithm? So if function f is convex and only locally smooth, or if the gradient is locally Lipschitz. Local Lipschitz means it's Lipschitz on the bounded region. For instance, like exponential that I mentioned in the beginning, and I said that it is not L smooth function, but locally, of course, because it's every time you take locally, it's bounded region. So on the bounded region, almost everything will be nice and Lipschitz and so on. So this thing is covered now. So we can assume even more. So what we can prove? We can prove that sequence xk converges to solution. And now it's a bit weird what is written. So it's not fxk now, because we cannot prove it for the last iterate, but we can show it for the best iterate. But since we track the iterates, it doesn't matter much. I mean, it would be better, of course, to prove it for the last iterate, but unfortunately, we don't have. Now the algorithm is not monotone because we can use these large step sizes, and of course function values can jump. But still, overall, it will perform well. And you have this rate, 1/k, which may look a bit disappointed. After all, this 1/k is exactly what gradient descent had, and so on. So it's like we wanted something different. But on the other hand, this is exactly what you should get, because your function f, maybe your curvature, Lipschitz constant doesn't change much. So actually, you cannot be that, even with this adaptivity thing, you cannot be that different from gradient descent, because there is just nothing to explore, nothing to gain from this procedure. Your step size will be still more or less fixed. So of course, and since gradient descent has this 1/k rate, you should get also 1/k rate. So for this kind of worst case functions. And the reason why we have 1/k rate is there is some constant in the nominator, and there is a sum of step sizes. And we show the step sizes are separated from 0. There are k of the step sizes, so that's why you have k, basically. But the interesting part in this statement, of course, is the sum of step sizes in the denominator, because at least intuitively, we hope that, yes, okay, so function has some curvature. We will explore this. We will use this information during convergence. So most likely our step size will be much larger than they were previously, let's say with a global estimate of L. And then because of that, the sum will increase much faster than just linearly with K. So that's our intuition, at least why in practice it should perform well. So, and to show this, for illustration, let's consider a standard task. We would like to solve logistic regression with some electroregularization and some classical machine learning data sets. Not important at all. So we want to compare a gradient descent, the one we mentioned from the very beginning, because this function is L smooth, it's easy to compute. It's Lipschitz constant, so why not? The same we do for Nestor accelerated gradient descent, which is the orange line, and this our adaptive gradient descent, which is a green line. So as expected, Nestor is much faster than gradient descent, right? 1/k squared against 1/k. What is maybe not so expected that our adaptive gradient descent, this 1/k rate, still beats accelerated method. And of course, the reason for this is the sum of step sizes. So the blue line here on the right plot is 1/L, and this L is the best Lipschitz constant you can estimate here. So it was not cheating, it's just like a proper Lipschitz constant, the best constant you can estimate the stuff. And the green line is our step sizes alpha. And as you see, they start more or less from the same kind of value, but they increase, they reach some level and more or less oscillate next to this level. And on this level is basically they're 100 times larger than the usual step size, the standard step size, sometimes 1,000 times larger. So of course, this sum of step sizes increase much faster than just linearly, much faster even than k-square. And because of that, we got much faster conversions. Of course, you cannot predict in the beginning of before you try to solve the problem, how fast your step sizes will look like. You have no idea about this. But at least practically or post factum, you see that you understand why you converge so fast. Or maybe to show a bit different problem, much simpler. So we just want to compare gradient descent and adaptive gradient descent for a very simple function, x to the power 4. So x to the power 4, so it's a convex function. It is not L smooth, but for gradient descent, we can still pick step sizes so that there is a descent. And since this function is like this, it will converge with if your first step size is good enough, fixed one, then it will converge further away. The problem is that x to the power 4 is a very flat function. It's like this. So basically, and the solution, of course, is 0. So kind of closer to the solution, there is a potential to use much larger step size. But if you start from, let's say, vector 0.1, the only step size you can use has to be less or equal than 1. Let's say, I don't remember the constant, but let's say something like this. But next to the origin, you can use much larger step size, and you will still converge. But gradient descent doesn't have this property, right, to explore the step size, unless you use some line search and so on. So if you compare it like this, then gradient descent converge very slowly, because the initial step size, just to converge, it has to be large, and then it cannot change it to something else. It doesn't have this information. But adaptivity solves this problem super fast. And again, the reason is that step sizes also it starts from very small number. It increases to basically to infinity. That's why you have so fast convergence. Okay. So we rewrote the algorithm in a bit different form. Let's try to understand why it has this form. So instead of LK, I just write explicitly here to make it shorter, and theta k is this ratio of step size alpha k minus 1. So how usually people prove convergence of algorithms? One of the standard approaches is to introduce another function. It's called energy, let's say. It has some good properties. Let's say it's not negative or at least lower bounded. And you show that this function this energy is decreasing along iterates. If it's decreasing along iterates and it's lower bounded, then you can argue that your iterates most likely they are bounded. And if the sequence is bounded, then most likely you can just take a limit in your fixed point kind of equation, and then you can argue, then I converge to solution, and so on. This is kind of standard thing. It's a discrete approach. What you do with Lyapunov function for differential equation. It's like one-to-one correspondence. So let's do the same here. So our Lyapunov energy would be psi k, and our psi k is defined like follows. So very weird, I think. So this, we have xk plus 1 minus x star is a normal term to have a function for Lyapunov energy for gradient descent. Xk plus 1 minus xk is also normal, but this stuff is a bit weird. So for usual gradient descent, you have not fxk, but fxk plus 1, but here we have somehow fxk, and of course we have this weird coefficient that do not exist in standard analysis. So we would like to show that for this energy, we have psi k plus 1 is less or equal than psi k. And then everything would follow immediately, right? Because you have monotonicity of this stuff. It's not negative. So of course, you can just telescope this inequality and obtain boundedness and so on. Unfortunately, this inequality is not true how it's written, because if you just write one inequality, another, start to manipulate, there will be some extra terms. There will be one parenthesis, and there is another parenthesis, 2 terms. So this is unfortunate, of course. So a natural kind of like a desire is just to kill these two parentheses, to make them negative. So if we look at the first one, negativity of it, or the non-positivity, means that alpha k has to be less or equal than this red thing. Right? Because that's it. I mean, I hope it's clear, right? You have to just square it, and that's exactly how. So if alpha, because minimum of these two quantities means that basically alpha k is less or equal than this, and less or equal than the red one. So if alpha k satisfies this inequality, then the red one is done. It's non-positive, so we can discard it. The second one, fxk minus 1 minus f star, we cannot do anything, so only with these coefficients alpha k, theta k. And it's even easier also because of this notation, it's not clear immediately, but if alpha k is less or equal to this stuff, it basically means exactly what's written in the green parentheses. It's just one-to-one correspondence, but also squared and so on. But it's also the same. So basically, that's why we have these two strange updates. The red one, at least, is understandable because it has to kind of it must have some similarities with Lipschitz constant. But the first one is super weird, and it just comes from the analysis, just to make analysis work, because otherwise you cannot prove the things. You cannot telescope them make work. This is still not a full answer, right? We still have no intuition why this and not something else, or yeah, maybe we can control it in a much easier way, and it's not clear to us, but at least we know that if you have some control, the algorithm will work. Okay, so this is the algorithm, and so that was adaptive gradient descent, and now we have some open questions. So we already discussed this, but still the question is present. So this green bound, the first bound for alpha k necessarily, can we replace it with something simpler, something better? Maybe we can allow. It's clear that we must control how fast alpha k changes, but maybe we can control in a different way that allows much faster increase of step size. Second, we have this 2 in the denominator, right, in the red stuff, which is a bit annoying because we kind of know that step gradient descent works with 1 over L. And here is like 1 over 2L, basically. And it's like, of course, it's not a big deal since it's adaptive, and most likely it will be still larger than this 1 over L, like for sure. But somehow, if you just use for quadratic this function with identity, but nothing changes, basically, then it's a bit annoying because your step size will be 1 over 2 always instead of 1. So in that sense, so just from aesthetical point of view, it would be nice to have something like, so you will be able to have 1 over L step size here as well. And the third thing is this problem we studied was just unconstrained minimization problem, and its analysis was very, very, very kind of tightly controlled by the update. It was really like just for gradient descent. So it's not even clear whether it's possible to do for constrained minimization or for slightly more like more general update, like it's called additive composite optimization, where you have sum of two functions, where G is another nice convex function. We call it prox friendly. I will talk it in a minute. For this kind of problems. Or really, maybe this is just an artifact of gradient descent analysis, and you cannot do this anywhere else. Okay, so that's kind of questions we're interested in. So improvement number 1. This was the first version of gradient descent, right? With 2, exactly as we had before. So nothing changed. So surprisingly, you can change this 2 to square root of 2. And I know it looks like it's like, come on, who cares? Which is true, no one cares. Like in terms of performance, it won't be that much of a difference because here it's LK that makes everything work. This 2 over square. Of course, it will be slightly faster, but like not super important. It's important probably that we can do this because it's gradient descent. It's very simple algorithm. There are not many things to play with, right? It's like just very, very plain. So it was surprising that you can still kind of try to play with these inequalities to make it even better, tighter, because previous approach is not that we will lose with something. We use all the inequalities like in the right way and so on, and still it was not clear how to make it. So with the square root of 2, the analysis becomes more complicated, ugly, but in the same time tighter. So you can get it. Even better, now the second version would be more complicated, so you don't need to look at it very, very carefully. So it's the same, but the update for alpha k now is a bit weird. So we change the first term like this, it becomes uglier, and this stuff became uglier. And it's really not important to understand what's going on. The only important here is the message that if we want to use alpha k 1 or L, you remember that was our motivation, right? We wanted to we didn't like this 2, now we don't like the square root of 2, and we were interested whether 1 over L is possible. So here it's not possible. And it's not, I understand that it's not clear still from this update why it is possible, but you can show that yes, this stuff, this notation means that it's a maximum from this quantity and 0. Because we take square root, so it cannot be negative. But this stuff allows to use fixed steps as 1 over L. So we have all the previous analysis and so on. And although this bound may look like now it's much worse, before it was clear that step size can increase. It's 1 plus something multiplied by the previous step size. Here it's even not clear, right? Because 2 or 3 plus something multiplied by step size might be less than 1. So it's even more complicated to show that step size can increase, and the summation of step size is also good enough, and so on. But still, in the end, you can do it. Okay, so this is like first improvement, second improvement. Finally, let's talk about composite minimization. So now we have sum of 2 functions, f and g. F is the same as before, it's convex differentiable, and g is convex or semi-continuous and prox-friendly. And by prox-friendly, it means that this operator, some strange operator, prox of g plus some regularizer, is easy to compute. And for many practical problems, we have an explicit form how to compute this prox. For instance, if our function g is an indicator function, 0 when x belongs to the set, closed convex set, and plus infinity otherwise, then this proximal becomes just a projection. So this projection, I hope it's clear, right? It's straightforward. And if you don't know what is prox, it's just a generalization, basically, of the projection to some simple convex functions. Something like that. For instance, if it's L1 norm, we have an explicit form, and so on. So it's very, very popular. So it would be kind of nice and very natural to try to extend this algorithm for this kind of problem. And it may look like it has to be trivial, because in general, if you have gradient descent, the analysis of the proximal gradient descent more or less the same is acceleration. So it's clear how to do it. Unfortunately, it's not the case here. So we have these 2 versions of algorithm, of improvement for adaptive gradient descent. And the short answer that actually you can do the same for proximal gradient method. So instead of just update, I will write prox here. So this is just gradient descent with these updates. And the point is that you can do it with prox. The drawback is that it's super non-trivial. The analysis is ugly and very long, and like if you can show analysis of gradient descent in the class, like no problems, not complicated, like very easy. So with proximal gradient descent, probably you cannot. It will take much more time, and students will be bored. Somehow I feel it. So that was the result of a recent paper. There is also a nice paper of Puyalot that also have a proximal extension. They use co-coercitivity also, and you may be also interested in the result. Okay, so that was okay. Probably a good point of view to remember. If we consider a continuous gradient flow, meaning that we have a function f, and we would like to solve a differential equation. So x prime equals to the minus gradient, and we start from x0. So this is called gradient flow, and so theoretically, if you work with it, it's always better because, for instance, this gradient descent, you have still something to work with. You need this smoothness and so on. Here it's like you don't need to assume much. You need just local Lipschitzness of gradient, and you immediately have existent uniqueness, and you don't care here about step size. There is no step size, and the proof also follows just like few lines, and you will have a proof that it converges, the rate, and so on. So it's like much easier to work with. But in practice, of course, if you want to do something with this gradient flow, either to implement or whatever, you have to discretize it. And different discretization lead to different algorithms. So one discretization leads to gradient descent. So now kind of we have the thing that this adaptive gradient descent, basically, which I rewrote it as the same algorithm that we were talking about. This is basically the way how to discretize the scheme. Because with this one, you also don't care about step sizes. Like the step formula for step size is explicit here. So in some sense, you also don't care about step size issue, and it also converges under exactly the same assumption as a classical gradient flow, local Lipschitzness of gradient and convexity. So there is like one-to-one correspondence, what was in the continuous case and now in the discrete case, which is kind of nice. Any questions so far? Okay.
May I have a question, please?
Yep.
Could you remind, please, what is theta in the step size?
Is theta?
Yes, theta, it was on one of the previous slides.
Yeah, this is a ratio between alpha k minus 1 and alpha k minus 2. So I will show you. Yep, let me see. Yep. So alpha k divided by alpha k minus 1. So just ratio between the current one and the previous one. Okay. Yeah, so that's why here I didn't write it, because I anticipated that someone might not remember what is like all these letters. Okay, that was all that we have with kind of theoretical analysis. Everything that we have some at least partial explanation or whatever, and some and proofs. And we have like two solutions. Either we quickly go through some heuristics if you have time, or we can just jump to conclusions. So do we have some time for?
Yes, we have time.
Okay, perfect. So in terms of heuristics, so one thing probably the most natural thing to ask is, since I mentioned gradient descent and next algorithm was as accelerated gradient descent, so it would be kind of very, very, very clear to do the same for acceleration. Here and also in the paper we had this result for strongly convex, and for this kind of functions, acceleration had the form also of Nestor had the form the same I wrote before, where beta is this strange kind of coefficient. It requires to know Lipschitz constant, and it requires to know mu, the strong convexity kind of parameter. So a good thing is, and since it's a strongly convex function, of course we should have a linear convergence. So, and this L over mu, the conditional number, is important here, right? For gradient descent, it was L over mu, and if it's accelerated, it will be square root of L over mu. L over mu can be super large, so taking square root is much, much, much better. So this is kind of the result, and again, you cannot improve this square root of L over mu. Okay, what is nice that we know already from gradient descent analysis how to estimate this Lipschitz constant locally, right? We use LK along the iterate every time. So kind of, what about mu, right? It's also some other constant, like maybe it has nothing to do with L, most likely. So what can we do with it? So if you know that function is strongly convex, then we can consider its conjugate dual or Fenkel-Lejeune conjugate function. I'm not going to give a definition, but it's basically the most important operation in convex analysis. And we know that this strong, by duality, strong convexity is corresponding to smoothness and vice versa, because it's like just inverse to each other. So we know that F star is 1 over mu smoothness. So we can use the same approach that we use to estimate L locally. Now we can use to estimate this mu parameter in the dual space. Because in the dual space, our gradients become primal vectors and our iterates become dual vectors, like the opposite thing. So we can play with it. And the algorithm in the left is terrible, and you don't even need to look at it. But the thing is, we just estimated LK for one thing, and we estimated mu k, which is basically reversed because it's dual vectors become primal and vice versa. We substitute in the formula of gradient descent, adaptive gradient descent, and that's it. So it only looks ugly, but it's just the same. We do double thing here for both things. And we use some two because for strong convexity requires some slightly more conservative thing. And so that was the same problem as before, because that problem was strongly convex. This was just not explored enough because the strong convexity was small enough. But so the three lines were the same as before. So if you add this red one, it's adaptive gradient descent with acceleration. We don't have theory that backups this, but it performs like super fast, like much better than even gradient descent. We have no explanation to this, but at least it works, and it's super interesting whether one can prove something like this. So that's what we mean by adaptivity for accelerated gradient descent. Okay, next thing is to try to do stochastic versions, of course, right? Everyone is doing now stochastic things. So if you have a sum of many functions, Fi, computing one gradient, full gradient F is expensive. So people do SGD. So instead of instead of computing full gradient, they sample one index CK and do gradient descent on this index CK, let's say. So in practice, people just take small alpha k, no one cares. In theory, you have to tend alpha k to 0 to have convergence of iterates, but in practice, we don't need to solve this problem to high accuracy. And basically, that's it. So all other stuff was today about how to estimate this alpha k. The step size for this kind of analysis algorithm is also called learning rate. So how to estimate it. So let's do something with Lipschitz constant just in the same way as we did before. So we sample psi k, we estimate Lipschitz constant k. Now look, we have to be more careful because we have to compute for this given new sample gradient, we have to compute gradient at the previous point, because the previous gradient has nothing to do with this current gradient. They were just stochastic. So this becomes more expensive in general, right? It's like we have to compute two gradients instead of one. So that's a drawback. And then we estimate alpha k basically in the same way as before, but we introduce some parameters beta, gamma, just to have, we are going to do it with some experiments with neural networks. Obviously, we would like to have some way to tune something because not clear what's going on. So that's why we would like to have some flexibility. Basically, that's it. So again, we don't have any guarantees for this kind of stuff, but why not? Why not to try it? And yeah, we do this SGD update, and it's the same as before. So the kind of experiments we have, just briefly, that's the main update for stepsize alpha k, and this is our update for xk. The same. So I just wrote the algorithm in 2 lines without much explanation. And so we test this algorithm compared with like state of the art, at least state of the art a few years back on the ResNet on the CIFAR dataset. So we compared it with SGD, with Adam, and different versions of adaptive SGD with different ways. So what was interesting, so as I said, although these results given in epochs, they're not super correct because our epoch was twice as epoch of, let's say, SGD, right? Because we have to compute 2 gradients per iteration. So that's basically what is expensive here. On the other hand, it was kind of interesting to see that if you were able to tune this parameter beta and gamma well, we could beat like state-of-the-art SGD on the test accuracy. Like the red line on the second plot, the red line was better than the blue one, let's say. The question, of course, is how to tune this, because the point for us is to do adaptive version of SGD, but still there was some room to tune, which is of course not desirable. What was interesting also that if you plot step sizes or learning rate, then it was weird that the step sizes increased so much and the algorithm still performed pretty well. And so they increased, then they stayed stable for a long time, and then they just like went down, more or less when stabilization happens, then kind of they started to decrease, which also, we cannot explain this behavior, we have no idea. It was just interesting to observe it. Okay, so to conclude, today we learned something, I hope, about adaptive first-order methods, and just a few key messages. So they use local information, they're easy to implement, we don't need to tune anything. Usually they're fast in practice, as we saw in the experiments, and in both papers there are many more experiments you can check, or you can check the code and try it on your own. And the important open question is that they are faster in practice, as we discussed, but it would be nice to prove in which scenarios in advance they must be proved faster. So instead of this 1/k rate, worst case, it would be better if there was some rate that depends on your problem, on your parameters, on the data set, and then you can say for sure it will be faster than gradient descent because of something. That's an interesting open question that we are working on. Thanks a lot. I still hope there will be some questions.
Yes, thank you very much. Are there questions from the audience? Just chime in. Maybe I can start with one. So can you quickly explain what happens when you don't do this check that the step size is not growing too fast? Why is the algorithm not working then in theory?
It's just because it's easy to construct the example of it's basically. I think maybe it will work even with a Huber function, but our example was not Huber function, but also look like this, where step size increase too fast, and then basically the outcome just diverge. You can make the iterate jump in a particular way, so there is no way to kind of go back. Somehow we don't understand why this like we have to, but it's relatively easy to construct this function. So it's just a quadratic, and then it's just almost linear. And because it's almost linear, the step size can be very, very large. And just because of that, it's like it jumps, instead of going down, it goes up.
I understand.
Something like this, but probably it's not the best explanation.
But in the experiments, you did explicitly control for this.
In the experiments, we always have a proper update.
Yes. And do you have an intuition if it's really needed?
But what do you mean? I mean,
you mentioned that it will probably work in practice without the.
I mean, most likely your function won't be as in the contra example. So most likely with your function, it will never happen because you have some particular problem to solve. So most likely it won't happen. So that's why, I mean, most likely you won't experience this in practice, of course. But if you want to prove something, unfortunately, then the thing becomes more complicated. So that's something.
Yes. Are there any more questions?
I'll ask a question. So are there some sort of, okay, I'm not sure this is it's an easy question to answer, but like could the algorithm be, is there some sort of like dynamical view of this algorithm? Like
what does it mean? What do you mean by dynamical?
Like can I sort of view this as a discretization of some like maybe a ODE kind of thing? Maybe not this particular algorithm, but a simplified version of this algorithm. So this algorithm is quite has quite complicated like choices of the how you adapt the how you update the step sizes. But like could maybe a simpler version of this adaptive method, could it be? Is there some sort of like a continuous analog of this algorithm that maybe
I think that's a good question, and that's why you still see my slides?
Yeah, it is on. It's on.
Yeah. So that's why basically I mentioned this discretization of gradient flow.
Yes.
Because somehow I also feel that, of course, it's well known that gradient descent is just a discretization of gradient flow. And we wanted to kind of to make it clear the connection of the step sizes from the grid, like somehow maybe there is deeper connection, how the step sizes come from gradient flow. We were not able to show it. So for us, it's just like probably like interesting fact that there is a way to discretize it, the classical gradient flow, so that there is like one-to-one correspondence in terms of assumption and in terms of result. But why exactly this update? Like, I don't think it's possible to explain it with the gradient flow or some other.
Maybe this not if I don't use this update, but maybe a simpler version update that sort of tries to mimic what you want to do. I mean,
maybe we were not successful in that. We also thinking how to connect it to the continuous dynamics in the sense.
Okay, it'd be interesting to see. I don't know. It's somehow like this continuous dynamics will give some very nice intuition about why this is much faster.
I don't know. Maybe it's just not our field of expertise. So for us, it would be more interesting to just understand the update for alpha k and how to explain this continuous dynamic, why it is fast in practice. That I don't know whether it's possible. Because it seems like it's the sum of step sizes that matter.
Okay. What about in the stochastic version? Like you mentioned some. I don't think I followed this, but like you mentioned something about the test error. Is there somehow like the answers from the iterates of the algorithm? Are they somehow finding something better solutions among possible minima? I don't know.
No, I mean, to be fair, it's neural networks, right? Nothing is convex, nothing. So we have no idea. It just.
Okay.
It's hard to test what kind of solutions they find. And to be fair, it's not about function values, right? Or gradient. It's about train like test accuracies, like how good your prediction in the second plot.
So
it's the first plot. It's the first plot is about function values.
Yes, that's right. Yeah.
So still it's like not clear at all how much you can say about how good your optimization problem is and so on. So I don't think we can say much.
Okay. Thanks.
Great. Then, if there are no further questions, let's thank the speaker again.
May I
yes,
ask
go ahead.
As far as I know, Konstantin Mishchenko also has some other papers on adaptive step sizes, but do I understand it correctly that he like goes the Adagrad way, and you here try to estimate kind of Lipschitz constant?
Yes, I think it's like in one sentence, it's exactly the description. In other papers, he tried to use this Adagrad stuff, and in Adagrad stuff, the good estimator depends on the, let's say, the distance from the initial point to the solution from the current point to the solution, and you don't have no idea about this kind of thing. So you would like to work with that stuff. And in the end, of course, there is always connection because that stuff depends on Lipschitz constant and so on, but that's the Adagrad approach. And here it's more, let's say standard gradient descent analysis. So you have this 1 over L, and you change 1 over L over 1 over LK. And then you think what else you need to make the algorithm to make it work.
Okay, thank you.
Okay, then we thank the speaker again. Very nice talk, and we'll see each other again in 3 weeks.
Thanks a lot for the